Okay, so now we're going to start with the second tutorial. Excuse me. In this case, the tutorial we're going to mostly focus on getting data in to R, and then just doing a few basic data manipulations like subsetting, sorting, merging. We're not going to go through a lot of detail of it. The rest I'll probably let you sort of take a look at, and then there's some specific things. And my hope is this will take about 20 to 25 minutes to run through it. All right, so if you scroll down to section 1 in this tutorial, and this is up on the class website, our introductory tutorial part 2, it says 2011, but it's for 2012. Often, sometimes, although you already did an exercise in class, sometimes the most difficult thing is to get R to read your data. It's just a useful thing. So there's a couple things to suggest. When you're starting with a spreadsheet program like Excel or OpenOffice or Numbers, a couple of suggestions. First of all, for missing data, make sure that the cells are empty. Do not have some kind of dummy character like a dot or NA. Just leave it blank. R will handle that, and there'll be lots of ways of doing it. Make sure that your column headings, if you do have headers, are clear, like sex or log.femur.length, for instance. Just something very clear. Try not to have spaces between them. R will fill them in with dots, but it's up to you to figure out if that's what you want to do. There's lots of different ways of doing it. R can read in lots and lots of different things. I'm just going to show you a couple. I'll let you explore things for more complicated data. We're really just going to use, in this case, read.csv, which is one particular function, but which is itself a special case of the read.table functions. And so keep in mind that this is the read.table or read.csv are the ones we're going to look at. Okay, so what that means is that if you are using something like Excel, what you want to do is go in Excel to File, Save As, and you'll see one with an extension .csv. That's often the easiest one to do, the least likely to have screw-ups, as long as you're not using commas for decimal places, which some people use. So some things. So do make sure you do that. So the first thing you need to do, we talked briefly about this today, is to set your working directories. And so people have lots of different ways of doing this, but I organize my projects around particular folders. So for a particular set of projects that I'm doing a particular project on a particular subject, I have a folder that contains both the R scripts, data sets, and any output. So it's all in the same place. That works for me. Other people have all their scripts in one place, all their data in another. Do what works best for you, or if you're using a database server, there's whole other approaches which we won't discuss in this class to do that. In my case, what we're going to do is grab, before we even grab the data set, we're going to go into the working directory. So setwd is for set working directory, and this function just basically sets the working directory in which R should be looking. In this particular case, it says for me, well, this is if I had a Windows machine, which I don't, but it would look in documents and settings and so on. We'll actually go and see that with Unix. You can use the Unix style slashes even in Windows, as you see here, or you can use the Windows DOS slashes, but you actually have to use double slashes. I don't know why that is. That's just one of the things. Also, you can use the GUI directly, and under Windows, using Windows, you can go to the R GUI, go to File, and change directory. That's sufficient as well. And there's ways of doing it with the command prompt in Windows. I'll let you DOS people take a look at that. It's less relevant in general. For Mac users or any sort of Unix-based system, just very much like we would do for anything else in Unix. We're just setting a working directory, basically just calling the directory directly. So here, going into my home folder, and I have a set of folders set apart. So I'll just call that, and again with the R GUI, I use the Apple return to do that. In the Windows, that's a Control R. If you want to know that it's worked, one of the things you can do is use this getwd, which is for get working directory. And that'll just confirm that you're in the right directory. And actually, you can see the contents in your directory from here. And there's many other ways of accessing through the basic systems. And this just lets you know of all of the files in this folder. There's some other alternatives like file.choose and scan, which reads data into vectors or lists. I should let you know that these read.csv that we're about to use, or read.table, that whole family of things actually does a bunch of things. It first of all opens a connection to the file, reads the files in or scans them in line by line, and then closes the connection. But thankfully, R has made it very easy to avoid having to be doing the open, read, and then close. The read dot functions do basically all of that. So once we've done that, since we've already set our working directory, we're just going to grab some data. This is some biological data of mine from a paper from a number of years ago. It's not really important. In this case, what it does, it's just fruit fly data. And the data file was called dll.csv in the working directory. And it has headers, so that means each column has a name. So we specify headers equals t or headers equals true. And then I'm just going to call that dll.data. And that reads it in. Okay, now like I mentioned in class, you read in the data, but you want to double check it and make sure everything looks good. And so there's a couple of things that you should definitely do. And I'm going to skip over this read.table, but you have an example sort of explaining it here. There's a number of things you can do. First of all, you can either use the edit or fix function, and that actually provides a spreadsheet to examine the data. So that's useful to see if there's any missing values that you want to encode. And if you do that, you actually get this big spreadsheet like editor that you can look at. There's other things that we want to do. So the first thing to do that I like to do is I start with the structure function, so str, and I look at the data frame, and it gives you a whole bunch of things. So it tells you, first of all, the class of this object. So we've created a data frame object, which is what we want, how many observations there are. There's 1973 observations of 8 variables, so that means 1973 rows, 8 columns. And for each column, it tells us its name. So here's replicate, line, genotype, temp, femur, femur, tibia, tarsus, and SCT. SCT stands for sex comb teeth, which is a secondary sexual trait on Drosophila. We can look at them and we see the classes for each of those columns. Most are numbers. Line and genotype are both factors because they're actually categorical, they're strings essentially, and it assumes that with strings what you want to do is have them as factors. You're going to use them for statistics, and factors are a way of having these discrete levels in statistics that we'll come back to. So it turns out in our cases we'll see there are a couple of other things that we're going to want to transform. Not all of these are the object types that we want, so we'll come back and fix that. But before we do that, we just want to make sure everything makes sense. So one thing is, are the number of observations right? So you can compare that to your original spreadsheet, or just count the number of lines in the file if you're just on Unix. The other thing you can do is actually, to make sure everything looks sensible, you can use the summary command. And what summary does for a data sheet, and it's kind of messy on this screen because I try to make everything very big, hopefully for the screencast, is for each of the numerical variables, it's going to give you the minimum, the maximum, the first and, I can't remember if it's the first and third quartile, and the median and mean. And you can use those to sort of spot, are they numerically, do they make sense? Do they seem like the right numbers? For factors, so in this case like genotype, which has 2 factor levels, DLL and WT, which are 2 different genotypic levels, it gives you the count of number of individuals with each of those. Again, providing you some useful summary information. NAs down here tells you how many missing values there are in the data set. So there's 25 missing values for the SCT column, 17 over here for the tarsus. Well, that's great. Head and tail do exactly what they do in Unix. They'll give you head by default gives you the first 6 observations. You can specify how many you want it to look at. So for all of the variables we look at, here are the first 6 observations. They look sensible. They look like they're in the right order. Nothing seems really wonky. We do the same thing for tail. Again, there's some missing data, but besides that, everything looks pretty sensible. And of course, we already know what this is because we saw this with the str function, but we can look at the dimensions, 1973 rows, 8 columns. Okay. We've already seen this, but we can obviously ask the class. Well, we know that the class for DLL data is going to be a data frame. But as I mentioned to you before, one of the important things to remember about data frames as a data structure is that it's actually just a list, but it's got some special features. But you can actually access things in the data frame as you would with a list or as you would with a matrix, which is really convenient. Names is a useful thing to have. That's just going to give you the names of the columns. You can even use it to rename things, and so on. And if we wanted to look at specific columns of data, we could do like we would for a list, go dll.data $genotype. Genotype being in case one of the columns, that'd be one way of looking at all that. And we can look at the summary of that and so on. We won't do that here. We can, if need be, extract both row names and column names. If that's useful for you, you can do it. We're not going to do it right now, but it's something that sometimes can come in handy. So one thing I want to warn you against is one of the tricks that you'll often see in our books is to use the attach function. What attach does is it sort of creates a access to all of the data in such a way that instead of having to call the data frame itself, the object name, $, whatever variable you're interested in, sort of creates a static copy of it in R. So instead of having to go dll.data $SCT to extract the SCT variable, you could just go SCT. The problem is it's static. So if you make any changes to, say, the original one, the original data frame, that will not influence the ones that have been attached. Similarly, if you change the attached variable anyway, it doesn't change the other one, and so it can cause confusion. In general, you don't want to use it. The other problem is, well, everybody says, well, there's this detach function as well. Well, actually, detach sometimes misbehaves, so I would just, in general, suggest not using it. An alternative to use, if you're going to have to use anything like this, because sometimes you're going to be calling lots of variables from within a particular object, you can use the with function. So you're basically saying with, in this case, with dll.data, so calling the object, and then whatever you need to do. And so it knows for this line, as you're calling it, that you mean whenever you call whatever variable, it should look in that object, in this case in the dll.data. Now if we actually do this, instead of giving us the mean number of sex comb teeth like we'd want, mean of SCT, you get NA. So that's not so useful. Well, what's going on? We'll come back to that later, but basically that's because by default the function mean, its default is when there's missing data to basically just report missing data for everything. So it's letting you know there is missing data and you have to make a decision about how you want to deal with that, which is quite trivial to do. One thing that's always quite useful to do is to use the table function to really, again, look at what do you really have in terms of sample sizes across treatments and levels and things like that. Sort of a good way of looking at your data. So again, we're going to look at our data, but with respect to combinations of things. So we're using this colon operator here, which is essentially, it's going to be the interaction operator, but it's going to give us all possible combinations of line and genotype. These are two different factors here that we have, and give us the numbers of observations for each of those. So again, because of how big I've made my screen, it's not so pretty here, but it basically says for each possible combination how many observations we have. So how many fruit flies have we measured? And for some of them, there's lots. Some of them, like this one, there's only 4 observations. That means we only measured it on 4 flies. Sorry, that's not covering. It's not highlighting it the way I'd like it to. And I think it may not show the ones with zeros. There's actually a couple of cases where there's 0. So it gives you an idea that this data is what we'd call unbalanced. In this case, incredibly unbalanced. What we mean by that is we do not have equal numbers of observations across all possible combinations of treatments. And that always creates some difficulties with estimation. So what do we do, though, if we know we have some missing data? We saw the NAs before. So how do we deal with that? And that's a really constant and important question in most empirical sciences, but in particular in biology, where often you are limited by the samples you can get, and some of them may be damaged, for instance. It's a very common problem, but it happens in all sorts of sciences as well. So one approach, and we're going to use that a lot in this class, but if you have lots of missing data, please come talk to me. I'll make some suggestions, because it in itself is quite a big field of how to deal with this problem. For the moment, we're just going to use a particular function called na.omit. And this is kind of the nuclear option for missing data. Basically, you say any row that has any kind of missing data at all, we just remove the entire row. So that's a pretty extreme thing to do. because even if every variable but one has data, only one variable of all the ones you have has any missing data for a particular observation, it will still remove it. For now, it's going to be fine, but do keep that in mind. That's not always the smartest thing to do, and it can be pretty extreme. So we'll call this dll.data.vetted, run it, and what this does, if we now look at the new data frame, we have 1918 observations, still 8 columns, versus the original one, which I believe was 1960 or 1973. So we lost quite a number of observations there using this approach. So do keep that in mind. Is that really how you want to deal with it? And there's some other options, and you can actually just use !na.emit and take a look at it. Often it's smarter, instead of doing that for the whole data set, you just do it as needed. Keep the whole set of data and just remove things as needed. So here I've put the na.omit just here. So it's only doing it for this particular column in this particular and this particular instance, and it makes no permanent change to the original data set. So dll.data, if we checked, would still have 1973 observations. All right. So one of the most common things we have to do in statistical analysis is the data, because of the way we've coded it, may be represented, say, as a number, but we really want it to be a factor, or vice versa. So again, if we take a look at the structure of the data set, well, replicate is numerical, line and genotype are factors, temperatures is numerical, and the rest of the things are also numbers. Well, it actually turns out in this particular case that temperature, for a variety of reasons, experimentally we want to treat as a factor. We don't want to make statements that 25 is greater than 18, even though it is in terms of Celsius, for a number of reasons. As 2 levels, we don't want to represent it that way. Similarly, replicate here, there's 2 replicates, 1 and 2, but there's not really ordering to them, 1 versus 2. There's no particular meaning to it other than our arbitrary assignment in this case. So in this case, because of that, we're going to change them from being the original numeric variables to a different type. So we're storing them differently. In this case, we're going to store them as factor levels, which actually is stored numerically, but it's done in such a way that there's no ordering. You won't see that, though. You won't, unless you delve deep into it. You'll actually see it coded as characters. So all we do here is we are just overwriting the original variables, so dll.data, $temp, and similar for replicate. We're just overwriting them with the same data, but just saying factor, which basically is coercing it into a factor. And so we just run those. If we now take a look, now replicate, line, genotype, and temp are all factors, with the remaining variables all being still numeric. Potentially, after I've made these changes, maybe I'd consider using attach. In general, I don't do that, though. Now that we've done this, we can maybe get a better sense of any missing observations, because we can actually make this interaction between line, genotype, and temp. And again, there's going to be a big table that's not going to look very pretty with the way I've set it up. Now you can actually see some clear zeros, so cells that have 0, in this case, this particular combination and several other ones. And that's going to be important when we think about how we do an analysis. Okay, check how we're doing on time. We're at 18 minutes, so I'll go for about just another couple of minutes. So the next thing that we'll want to do often is manipulate and extract data from the data frame object. So sometimes we only want to analyze a subset, or do particular things to subsets. And there's, as you're going to see, lots and lots of ways of doing it. One particular thing we could do is say we only wanted to extract one particular column, say the column we wanted to, we only want to extract a subset. Let's say we only wanted to extract a subset of the data where genotypic value was equal to this, DLL, which is one of the genotypes. So what we're basically doing is we go into our original data frame and then say, using the indexing, we basically say, find all cases where genotype is exactly equal to DLL using the double equals operator. And again, we're doing that for all rows, so we do it that way. So along rows and then for all possible columns. So it indexes along the rows. And we do that, and now we're going to have a new, much smaller data set this case, 871 observations. You could look at the head of it, the first 6 observations, and not surprisingly, all the values are DLL. So there is another function that can do this, which acts just as a wrapper for this function for doing these things in the index. And even the indexing is actually a function in R. I'm not going to go into that here. You could do the same thing using the subset function like this. I tend not to use it because for more complicated operations, this can be not so useful. But you could just as well do that. And then we could do, say, something like using that to look. This is a really unpretty graph. I'm not really interested in this case, but you could graph them separately. There's far better ways of doing this, though, that we'll talk about later in the class. And I won't go through them here. You can just see that there's some alternative ways of extracting data. So if we wanted to extract particular columns, we could do it like this by calling column names, as you see here. And I've listed a couple of other options, which you can just take. We did this in class as well. And you can, of course, just use if it's column number 3 for SCT or whatever it is. I think actually in this case it was column 8. You could just use 8 in that case. That would work just as well. And like I said, we can combine different variables to manage our subsetting. So instead of just trying to subset just based on genotype, if we wanted to look at particular combinations, in this case where genotype equaled DLL and temp equaled 25, we could just do exactly that using the ampersand. And not surprisingly, this will produce an even smaller data set, in this case about 425 observations. And one good thing to do is then double check that that we get the right number of observations out of it. So we go back to the original data and ask how many observations do we expect for that particular combination, and in fact it is 425. So 425 right here for that set of combinations. Okay, one thing you should know about this is that R has a kind of a funky little feature that the rest of us in the world will think is a bug. So levels is going to tell us how many different, for a given factor, how many different levels there are to that factor. So in our case of genotype was a factor with 2 levels, DLL and WT. For line, I think it has something like 27 different factors. This lists them all out, all the different names. And then, of course, if you want to know how many actual levels are all, you just use length on that. So you just take the vector, use that, treat it as a vector, and just look at the length of that. Well, that's great, and you could do that similarly for other variables like temp, and here you get 2 levels, 25 and 30. Now, what's so weird about that? Well, nothing, but if you remember, we created these subsets of data. So in this case, we created that subset which it had, we only pulled out the combinations that had genotype DLL and temperature being 25. We did that, and we had 425 observations, and we should only have, for temp, 1 level. We should only have 25. And yet, if we do this, it says we still have both. It says we have 25 and 30 in this data set, even though we've dropped all of those observations. So keeping all of these levels of the factor associated with the original object, so the original object DLL.data had both levels. And so even though you've removed those observations, it's still sort of in the data structure, keeps the memory of the fact that you used to have observations, even though it no longer has those observations, which is kind of a ridiculous thing in my mind. I'm sure they were thinking about something when they did it. There's a couple of ways of doing that, of getting rid of it. One is to use this drop levels factor, which basically says, well, when you do it, drop the levels that don't need to be used. Or the other way of doing it is just for that one particular variable, even though it's a factor, you call it factor again, and it basically looks through the observations for all the possible factor levels. And since even though it was originally keeping the fact that it has 2 levels, the fact that there was only observations for one of those levels, it sort of coerces this to a factor now with 1 level. And so that if we actually went levels, do I have that written here? No. So if we actually use levels for that data frame, SCT underscore DLL underscore 25 $TEMP, we run that, and now we see that there's only 1 level. We don't have, the 30 has been dropped. Okay, I think we'll end this one here, and then I'll come back up with a new one.